reinforces the link between matter and gravitation. Right, Olivier?
Faudrait pas qu'on perde du jour.
Please don't hesitate to mute yourself if you don't. You just entered the room.
C'est dans la boîte.
And so let me present you Olivier. Olivier did his master's degree and his PhD here at the Observatoire, his PhD under the supervision of Bertrand Chauvineau. Then he went for a short postdoc in Observatoire de Paris. And then he continued with another postdoc in Caltech JPL in the US. Then he came back here as a chargé de recherche from the Scientific Center of Monaco until 2020. And he is also an associated researcher in Artemis here at OCA, having his office at the Maison Jumelle. Am I correct, Olivier?
Yes, absolutely.
So it's a pleasure for us to have you, to hear you, to listen to you again. And please, the floor is yours for 50 minutes.
Thank you, Georges. I'm turning off my cell phone. So thank you, everyone, for attending this seminar. I will present nothing less than a new theory of relativity, which I propose to call Entangled Relativity, Relativité intriquée en français. And hopefully you'll get to understand why I chose that name. First thing first, it has nothing to do with quantum entanglement. So yeah, that's something that has to be said. I will start with some reminders. So many of you have already attended some of my seminars, and therefore you know that I don't do seminars without equations. So there will be several equations during this talk. I will try to convey what they mean, and you don't really have to understand them, but I will try to explain what they mean. But really, one cannot present this new theory without any equations, because basically at the popularization level, the theory won't be any different from general relativity. So it's really, the devil is in the details, and it's really in the details, the mathematical details, that you'll see what is different from this theory with respect to general relativity. So I'll do some reminders with the least action principle, then I'll present general relativity, then I'll show some basics of entangled relativity, the field equations, for instance. Then I'll present some results, which basically are just there to show that the theory is viable in the sense that it is consistent with observations. And then I'll finish with what is the most exciting, in my opinion, with the discussions. Okay, so first of all, work. Okay. This theory does not come out of the blue. It is the result of a decade of research that I started when I was at JPL in Pasadena. The first publication of the theory was in 2015 in Physics Letter B with a PhD student who was an intern in Artemis for 3 months, Henrik Ludwig. We proposed this theory, but I later figured that we missed a detail, which was actually a really important detail. And therefore, I published the final form of the theory in 2018. And actually, so the name entangled relativity is fairly new, because the name has appeared in the literature only this year, well, last year, 2020. Okay. So some reminders first. So here is, I'll talk about the least action principle. So the least action principle, basically, can you see the mouse when I move?
Yes.
Okay, cool. Okay, so basically you have an action and you have a Lagrangian density. And if you extremize this action, you get the field equation of the theory. So it is like in Lagrangian mechanics. So in Lagrangian mechanics, you define an action. You have a Lagrangian that depends on position and velocity. And when you maximize the action, you have the Euler-Lagrange equation that describes your system. So in field theory, that is the same thing, except that instead of having a Lagrangian, you have a Lagrangian density that instead of depending on the position and the velocity, it will depend on the field and its derivative. But when you do that, when you derive the Euler-Lagrange equation, you basically obtain the field equations. So for instance, there are a few examples, like general relativity in vacuum. The Lagrangian density is what we call the Ricci scalar. You derive it, you extremise the action, and you get the Einstein equation, the equation of general relativity in vacuum. So basically, whenever you hear about the Schwarzschild black hole or the Kerr black hole, those solutions are vacuum solutions, and therefore they are a solution of this simple equation here. So that's one example. Another example would be electronism in vacuum, which Lagrangian density would be equal to that guy, where F is the electronegative tensor. You extremise the action, you get the Maxwell equation. Many of you won't recognize Maxwell's equation here because you're probably not used to this form, but it's just an explicitly covariant way of writing at least part of the Maxwell's equations here. So don't worry, here you really have the usual Maxwell equation in vacuum. Okay, so now what do you do? What do we do when we want to have both at the same time, like curvature of space-time and matter, like for instance, electronism in a curved space-time? Well, we simply add the two. This is called the minimal coupling. Well, this is not exactly that easy. There's some details, but basically that's it. You add the two, and by adding the two, you'll recover the equation of general relativity here, which is slightly different from the one that you're used to. It's just because of the property of the electronegative tensor, but that details. Basically, this equation tells you that this is the matter, stress energy matter tensor. It tells you, and this is curvature. It tells you how matter, how space-time is curved due to matter. Can you hear me well? Because
it just interrupted for a bit, but yes, now yes.
Okay. Because I had a warning telling me that my internet connection was unstable. Unstable. Okay, so you get the equation of general relativity and the equation of electronism here. So you get both set of equations. Okay, so sorry. So the basically general relativity is a theory where matter tells space-time how to bend and space-time tells matter how to move. This is basically what general relativity tells you. And here is the actual action of general relativity, where unlike previously, I kept this constant not equal to 1. And this constant, which is a coupling constant between the two, between curvature and matter, is proportional to the constant of Newton here. So when you extremise the action, you get the equation of general relativity here. You get the conservation of the matter stress energy tensor, and you get all the matter fields equation that would come from this guy. Okay. The thing with general relativity, it has, in my opinion, 3 fundamental issues. The first issues being singularities. So you may have heard about the Penrose Theorem, for which Penrose got the Nobel Prize this year in physics. Basically, this theorem tells you that from the type of matter that we know that exists, and assuming general relativity, there must be some inside a black hole, there must be a singularity, which means that space-time itself breaks down. But the thing is that general relativity entirely relies on the existence of space-time. So it means that general relativity itself breaks down. So that's really puzzling, because if you follow the laws of general relativity, it tells you that the laws breaks down. So this is really something puzzling, and a lot of people have considered this proof as well, this theorem, sorry, as a proof. Sorry.
Go for it. Someone was unmuted.
Okay. So many people have considered this this theorem as a proof that general relativity was incomplete, and it was written in a Penrose paper, original paper, that it may mean that the laws of general relativity have to be modified. Or another possibility that many people are considering is that one has to take into account quantum gravity effects when you arrive at really high density, and this is what will prevent the appearance of this singularity. Okay, that's an issue of general relativity. Another issue is that space-time has no operational meaning beyond the Planck scale. What does that mean? Is that if you assume that the Heisenberg's principle is valid up to really high energy, then the issue with this principle is that if you want to probe scales that are smaller than the Planck scale, the amount of energy required to do that, thanks to this Heisenberg principle, would lead to the formation of black hole, and therefore you would not be able to probe any length below the Planck length. So it is like if there was really not any operational meaning of space-time below the Planck length. And this is the main reason for that, is because the size of black holes is related to the constant of Newton. As a fundamental constant in general relativity, it is a fundamental constant. And basically the size of black holes is 2 times g times the energy divided by c to the 4th. So if you put enough amounts in a distance that is shorter than the Planck length, you will form a black hole. And the issue is that if you want to put even more energy in order maybe to probe an even smaller scale, you form an even bigger black hole. So that really seems to indicate, and a lot of people have been arguing in that direction, that space-time is not elementary, it's not fundamental. There's something more deep underneath, and space-time itself would be emergent. That's something that is really shared by a lot of theoretical physicists at the moment. And last but not least, of the general relativity issue is that inertia can be defined from nothing, which means that general relativity does not satisfy Mach's principle of Einstein. So what is it? And this is a really this issue has been debated over several decades. It's really controversial because it has a philosophical appearance. Okay, so Einstein believed in the relativity of inertia. So in his paper called The Principle of General Relativity, he said that basically what drove him in order to find the theory of relativity was 3 principles. The first principle being the principle of covariance, basically telling you that the field equation should not depend on the coordinate system that you're using or depends on the observer. That's the first principle. The second principle tells you that inertia, inertia and gravity is the same thing, basically telling you that the metric defines inertia as well as gravity. That's the equivalence principle. And then the last principle, which is Mach's principle, he called it Mach's principle, which says that space-time is completely determined by the energy tensor of matter. And with this principle, according to the field equation, there can be no space-time without matter. And this was a really strong requirement from Einstein. He believed that it wouldn't be logical to have a vacuum solution of general relativity. And well, it turns out that general relativity does have vacuum solution, such as, for instance, the Schwarzschild metric, or the Kerr black hole metric, which are both vacuum solution. So he was so convinced that his theory wouldn't have a vacuum solution at first, that even when he first visited the United States in 1921, he said to the press, it was formerly believed that if all matter things disappeared out of the universe, time and space would be left. He was referring to the theory of Newton, of course, with space and time being there forever without moving, and stuff being inside this space and time. Though he continues by saying, according to relativity theory, however, time and space disappear together with the things. So it really shows that for him, it was clear that general relativity shouldn't allow for a vacuum solution. So why is that an issue? Why is that a logical issue? And again, this has been debated a lot, and it's kind of controversial as well. So the issue, in my opinion, is that frame dragging shouldn't be possible in an empty space-time. And yet, general relativity allows it. Why is that? So in general relativity, when you have rotating objects like the Earth, the rotation drags space-time itself with it. And therefore, you can do an experiment. For instance, you can send lasers around the Earth, one clockwise and the other counterclockwise, and the time in order to do the rotation won't be the same in one case and the other. And therefore, you can measure really the rotation. But in the solar system, this rotation can be measured with respect to the distant stars, which give you the frame, the celestial frame. Okay, so local measurements, you can do a local measurement of the rotation of the Earth, this frame dragging, and it turns out that it corresponds exactly to the rotation of the Earth with respect to distant stars. Well, the issue in general relativity is that you could have, say, a rotating black hole, for instance, in a universe that is empty otherwise, and still you can define a frame dragging, meaning that even though the black hole is not rotating with respect to anything at all, you can tell that it's rotating, and this doesn't make sense. Again, this is something really controversial. Some people disagree with that, but that's the main reason why Einstein thought that one of the reasons why Einstein thought that general relativity, a consistent theory of relativity, shouldn't allow for solution of vacuum. But it turns out general relativity allows for solution of vacuum. And it turns out that's the really reason why Einstein introduced the cosmological constant in the first place, because he knew that general relativity without a cosmological constant had a solution, which is a flat spacetime, the Minkowski spacetime, and so he would have a solution of vacuum. And he thought at first that introducing the cosmological constant will break this and would make that a vacuum solution wouldn't be possible in general relativity. Well, it turns out that de Sitter found a solution of his theory with a cosmological constant, but in vacuum otherwise. And Einstein was really not happy with that, because it meant that his understanding on one of the basic fundamental principle of a theory was not correct or was not fulfilled in general relativity. So he said, in response to de Sitter, to the paper of de Sitter, if the de Sitter solution were valid everywhere, it would show that the introduction of the lambda term does not fulfill the purpose I intended. Because, in my opinion, the general theory of relativity is a satisfying system only if it shows that the physical quality of space are completely determined by matter alone. Therefore, the G mu nu field must exist. That is, no space-time continuum is possible without matter that generates it. Okay. So now, the basics of entangled relativity. So as I said, from the popularization level, I'm already a bit late on schedule, sorry. From the popularization level, entangled relativity tells you that matter tells space-time how to bend, and space-time tells matter how to move. So basically, there's no difference with respect to general relativity. It's the same thing. And you have a 4-dimensional spacetime. What is general relativity? Well, it trades the usual additive coupling that you have between matter and curvature with a coupling constant to a pure multiplicative coupling given here without any coupling constant. So and again, this has nothing to do with quantum entanglement, at least as far as I can see now. But so one thing that people should know is that people who are used to deal with theories. Sorry. Okay. So people who are dealing with theories in general, the reaction to this term would be, oh, wait a second, this cannot work because we know that, well, when you have a square here, you should run into some kind of trouble. So the reaction usually is like, is to be really suspicious about this form. This really, you can tell by looking at it that it's not something that we're used to. And yeah, and this reaction actually is naive, as I'll show. Okay, so this is the equation of general relativity here. And as I said, you trade the additive coupling between curvature and matter, and you have this new pure multiplicative coupling. And this is the field equation that you get. So it's something more complicated. The left-hand side here would be the same as in general relativity. You still have the stress energy tensor here, except that instead of having a coupling constant in front of it, you would have a field, weird field. It looks awful. The first time that you see that, looks awful. And the same thing with the second term here. It's a complicated term. You don't really have any intuition of what it means. So it looks weird, at least. The good thing with this form is that now you cannot even define space-time without defining matter at the same time. Meaning it does not make sense. Unlike in general relativity, where you can study gravity in vacuum. You can just say that, okay, you have the reaction is the Ricci scalar and I'll study that. Here it's not even possible. You cannot even have definition of relativity without defining matter fields at the same time. And this is why I propose to call the theory entangled relativity, because now relativity becomes really entangled with the definition of matter fields. You cannot study one without studying the other. That's not possible. You have to study both at the same time. And one thing therefore is that inertia cannot be defined from nothing, because nothing is not something that is possible in theory. Okay, so it seems that this theory shows that the inertia cannot be defined from nothing in this theory. So that's a good thing. And we'll see for the two remaining big issue at the end of the talk. Okay, so now I apologize a bit because I'll still have to show some equations in order to actually simplify the discussion. One can show that this action here, this guy, entangled relativity, can be rewritten as this, meaning that this gives the same field equation as this. But the good thing with this guy here is that it looks like something that we are really used to deal with when we deal with alternative theories of gravity, because this is called a scalar tensor theory. It's a really specific one, but it's something that has been studied for decades, and therefore there's a lot of tools, there's a lot of understanding of stuff like that. So that's a really useful tool. Knowing that is really useful in order to study the theory. So here is the field equation. So assuming this Lagrangian density here, you have this equation, which looks a little bit more familiar for people who are used to it, with an equation on the scalar field, or this is called the scalar field, and conservation of the stress energy tensor. Anyway, you can show that indeed, if you derive the field equation with respect to a scalar field, you get this equation here. And if you inject that into the metric field equation, you recover indeed the metric field equation of the first Lagrangian density. So you have shown that the field equations are the same. Okay, so now the results. And again, those results are just meant to show that the theory is viable, meaning that it seems to be consistent with observations that I've checked so far, that we've checked so far, because we were several to do that. So first, general relativity turns out to be a limit of integral relativity. And how do we see that? Is because of this equation here. You see that if you're in a situation where this term is equal to this term, and I'll tell you later on when this happened, but if that happens to be the case, then the scalar field is not sourced. Therefore, a constant scalar field is a solution of the field equation. When this is the case, then this guy disappears. This guy is a constant, and therefore you just have a normalization of this constant here. But basically, you recover the equation of general relativity. And same thing here. This guy disappears because this is constant. And here you recover the usual stress energy tensor conservation. And therefore, you recover general relativity. So that's basically the main thing with this theory, is that whenever you're in a situation that you have this, and I'll tell you again later on when this happens, but whenever you have this, then you can recover exactly the equation of general relativity. So in other words, general relativity is just a limit of the theory whenever this happens to be true. Okay, so when does this happen? Well, it happens, for instance, for dust. Because dust, so this is called the on-shell matter Lagrangian. Dust basically is just the Lagrangian, the density Lagrangian of dust is simply the sum of the mass. So dust is just particles that are not interacting, that are not colliding. And the description of that is simply the sum of each mass in space-time. And this is given by minus the energy density, which turns out, of course, to be equal to the trace of the stress energy tensor. So you are exactly in the situation that I was mentioning previously. So the action for dust field is written this way. So you see, you have just a sum over masses. And it turns out that you can do a conformal, so this is a bit technical, but you can do a conformal transformation, and you get this equivalent action that turns out to be exactly general relativity. You have here, it's the Ricci scala of general relativity, and here is the coupling that you have in general relativity. And you have indeed this additional guy here, but it's not coupled to anything, so it lives its life without interacting with the rest. So you don't care about it, you can forget about it. And you get, with this conformal transformation, you show that you really have actually general relativity. It's like this theory is just, we call it a veiled version of general relativity, but it's equivalent to general relativity. So what it tells you that if the universe was only made of dust, then the theory of entangled relativity would be equivalent to the one of general relativity. There wouldn't be any difference between the two. And it's a good thing to realize that, because the universe is really well approximated by being made of dust. Like dark matter can be well approximated of being dust. Even the planets in the solar system, you can, at first approximation, assume that they are just dust, because it's just particles moving on Kepler orbits. So it's a good approximation. So it means that the theory seems to be, in good approximation, equivalent to general relativity, and which is a good thing. So cosmological evolution of the universe. Okay, cosmological evolution of the universe. Well, one can show that the phenomenology of the theory converges to the one of general relativity without a cosmological constant during the matter era. Because in the matter era, basically, the universe is dominated by dust. And you've seen that in the theory, when you have dust, basically the extra degree of freedom, the theory is not sourced, and therefore, basically, it freezes. So the scalar field here, no matter what it was doing before, the matter era, whether it has a really high dynamics or whatever, it will freeze directly as soon as you enter the matter era. But it turns out the Newton's constant is proportional to this guy. What it means that in the theory, the constant of Newton is not a fundamental constant, but it's actually the value of a field. And the actual value now is given by the evolution of the universe, is where the value is where the scalar field froze at the entrance of the matter era. Okay, what about post-Newtonian solution in the solar system, for instance? Okay, so now, unfortunately, one has to use an assumption in order to do some calculations. Otherwise, it would be too complicated. I mean, this assumption is that one has to assume. We first used the assumption that the rest mass energy density will be conserved, meaning that there are some form of mass which is conserved along the world line. So that's an assumption that may not be true. Basically, in order to test this assumption, one would have to derive it from first principle with the actual equations of say magneto-hydrodynamics at the microscopic level, then try to infer whether at the macroscopical level this would still be true. That's a bit complicated, and so. But anyway, if one assumes this conservative assumption, then there are two cases for entangled relativity. Either the on-shell matter Lagrangian is equal to minus the total energy density, and in that case, the scalar field, instead of being sourceless, will be sourced by pressure only. This is the reason why we call that the scalar field the pressure run, because it will be sourced only by pressure, meaning that whenever you're in a situation where pressure is weak, you shouldn't have any, you should have only weak deviation from general relativity. Whereas if you're in a situation that pressure is strong, then you could maybe expect strong departure from general relativity. But it turns out in the solar system, so what it means if you have this guy, the pressure on, it means that the metric of entangled relativity is equal to the metric of general relativity up to corrections that are of the order of the pressure divided by the energy density. But in the solar system, for instance, an order of magnitude for the Earth is 10 to the minus 10, meaning that this correction would be 10 to the minus 10 smaller in amplitude with respect to the first relativistic effects already, which are already pretty small compared to Newton effects, right? Okay, so it's really, really small. And that is if you have this, you use this assumption, which itself comes from this assumption here. But it turns out in entangled relativity, the same assumption here, and only in entangled relativity, as far as I know, for this kind of theory, you could also have Lm is equal to T, the trace of stress energy tensor. And if that happened to be the case, and again, this would have eventually to be derived from first principles, which is a tough thing to do, then you would get no source at all. And therefore, you would just recover exactly general relativity. There wouldn't be any difference. Okay, so for the Earth, in the solar system, this ratio here is pretty small, but okay, we know places in the universe where that's not the case, where pressure is really high, is actually comparable to the energy density, and that is for neutron stars. In neutron stars, we know, right? In neutron stars, we know that, yeah, there are really relativistic objects, and therefore we know that the pressure is comparable to the energy density in those objects. So we investigated this with Denis Arruga and Olivier Roussel. We assumed a simple equation of states for the nuclear matter, because what we wanted to see is to compare general relativity and entangled relativity, not to do a full really study. So we assume a simple equation of states. And we got those plots. So what are they? They are pretty common when you study neutron stars. So basically, each point represents a simulation. So the curve would be like a continuum of simulations. So here you have the mass in terms of solar masses, and here you have the central density. What tells you is that if you, for the two theories, in orange is general relativity and blue is entangled relativity, if you say you assume that you have a central density inside your neutron stars of 1,000 of this unit here, then the simulation tells you what would be the mass of this neutron star. That's the equation of general relativity, or the equation of entangled relativity, okay? Same thing here. Basically, each simulation will tell you for each mass, you will get a given radius, because assuming a specific equation of state in general relativity, for a given mass, you get a given radius for your compact object. Okay, so what can we see in those plots? Basically is that, roughly speaking, you have the same thing in entangled and general relativity, even though we've seen that it should be where entangled relativity deviates the most with respect to general relativity, because this is where pressure is really high, and we were expecting to see really big deviation from general relativity in those situations. So the maximal difference is basically 8% between the masses predicted by entangled relativity and general relativity. And one good thing to see as well is that the mass of entangled relativity are always heavier than the one predicted by general relativity. Okay. There is one way that may be used in order to test the theory, because the metric outside the neutron stars is slightly different in entangled relativity with respect to general relativity. In general relativity, you have a theorem known as the Birkhoff's theorem that tells you that outside a spherical object, you will always have the same metric for a given mass, of course. Whatever the object is, if you have a black hole or the Earth, provided that the Earth is totally round, you'll get exactly the same metric outside. And this metric will be the Schwarzschild metric. And the Schwarzschild metric, you can multiply the space-space component of the metric to the time-time component of the metric. My connection is still unstable. Can you hear me?
Yes.
Okay. So the space-space component of the metric times the time-time component of the metric, the Schwarzschild metric will tell you that it's a constant outside the object. So in this plot, the vertical lines are the radius of the different simulation, the different simulated neutron stars. There are 2 in general relativity and 2 in entangled relativity, which have the same mass. Plain line is general relativity, and you can see that indeed this product here, as soon as you're outside the object, it's a constant, and here as well. Okay, that's the Birkhoff's theorem. That's the property of the Schwarzschild metric. But it turns out it's slightly different in entangled relativity, and especially when, and the number here is the central density of the object. So you can see that here in yellow, for the highest central density, and therefore the most compact object, this is where you expect to have the highest deviation from general relativity. And you can see that indeed you don't have, when you exit, the metric outside the object is not simply a constant, but it decays, and the constant is an asymptotic, of course. But it means that the metric outside the object is slightly different from what you expect from general relativity. And this might be tested because there are observables that depend on this space-time metric, such as what we call the Shapiro delay, for instance. So this may be a way to test the theory. And one way potentially that will allow to test the theory would be with the observation of X-ray pulse profile emitted by hot spots on the surface of neutron stars with, for instance, the NICER instrument from NASA. So the idea is the following. You have your Newton star and a hotspot that emits X-ray pulses, X-ray. And because space-time is really curved around this really compact object, the trajectory of light is a bit weird. But it means that if you have this kind of guy, you can predict what you can model what kind of signal you expect depending on the curvature of space-time around this object. And this is a simulation that has been done by Denis Aruga. It's not published yet, but it tells you that basically you can do indeed this simulation of what you would expect from either general relativity or entangled relativity. And you see that you can expect either a small deviation or larger deviation, depending, of course, on the central density of the object. So the biggest the central density of the object is, the more the object deviates from what you would expect from general relativity. Okay, now what about black holes? Because after all, well, we've seen what we're now having more and more evidence of the fact that the black holes of general relativity looks pretty much we have evidence that the black holes in nature are well described by the black holes in general relativity, like the Schwarzschild black hole and the Kerr black hole. But those solutions in general relativity are a solution in vacuum. And I told you that in this theory, entangled relativity, you cannot have vacuum. You must, at the really beginning of your study, to define a matter field, because you cannot define space-time without defining matter field at the same time. So therefore, one has to check whether black holes in the theory are still consistent with what one expects from general relativity. And for that, you must work with specific matter fields. So we worked with electromagnetism, with a charged black hole. We basically derived the equation of a charged black hole. And this the issue with that is that it's more complicated to study black holes in the theory with respect to general relativity, because you have more equations to solve. In general relativity, if you are considering general relativity in vacuum, you only have the metric field equation to solve. Whereas if you have electronism in addition to, then you not only have the equation for the metric, but you also have the equation for the electromagnetic field. Therefore, you have more equations to solve, so it's a bit more difficult. But fortunately enough, there's again this trick of conformal transformation. It's a bit technical, so I won't enter into details. But basically, you can rewrite entangled relativity into this form. So this guy is still entangled relativity, but rewritten in another way. But it turns out that this guy, this Lagrangian density, is pretty much what was expected at the low energy limit from various string theories. And therefore, this kind of action, this kind of Lagrangian density has been studied a lot during the first superstring revolution, because basically people were trying to figure out what would look like black holes according to string theory. So that's really fortunate, because we can use those works in order to try to find a solution for this really specific theory. And this is what we did with Edison Santos, who some of you may know because he was a PhD student who spent a bit more than a year, I think, at the Observatoire 2 years ago, or 2 or 3 years ago now. And so we found a solution. So you don't have to really understand what it means, what are the R plus, R minus. We don't really care. What is interesting is that it tends to the usual Schwarzschild metric whenever the electromagnetic field goes to 0, meaning the charge go to 0. And we know that astrophysical black holes have pretty much no charge. So basically tells you that if the matter field goes to 0 without being equal to 0, you can go arbitrarily close to 0 without being equal to 0. But if it goes close to 0, as we expect should be the case for astrophysical situations, then you recover the usual Schwarzschild metric, meaning that the usual Schwarzschild metric is a good approximation of a spherical black holes in entangled relativity whenever the electromagnetic field goes to zero outside the black hole or inside the black hole. So it led us to two conjecture, which seems rather obvious from the field equations, although one would have to derive them carefully at the mathematical level in order to prove that that they are correct. But from looking at the field equation, it looks rather obvious. And the first conjecture would be that the usual Schwarzschild metric is a good approximation of spherical black holes in entangled relativity whenever matter fields outside the black hole goes to zero without being equal to zero. And second conjecture is that it should be the same basically for rotating a black hole, a Kerr, meaning that the Kerr black hole should be a good approximation of rotating black holes in entangled relativity. What happens beyond the event horizon remains to be studied, and I will talk a little bit about this later on. Okay, now gravitational waves, because after all, we've seen a lot of gravitational waves, and therefore we have to check whether gravitational waves in entangled relativity are consistent with observations. And this has been done by other teams, not talking about entangled relativity, but talking about this theory here, Einstein-Maxwell dilaton theory, which, as I said, basically is what is predicted by several low energy limit of string theories. And except that you have a coefficient here, alpha 0, alpha naught. And here is entangled relativity. So you can see that it's a specific case of this theory with alpha naught equal to 1 over 2 square root of 3. Okay, it's just a special case. And what they found is that basically from numerical study of merging black holes, that you don't see any difference between this theory and general relativity as soon as the charge of the black holes is small. But the thing is that we don't expect astrophysical black holes to be charged a lot, maybe a little, because as soon as they have an electron, they will have a small charge, but not a lot. So it means that this theory should not be constrained by gravitational waveforms. You should expect the same thing as general relativity. And it has been confirmed by analytical study as well. So what it means is that it appears that gravitational waves from the merger of binary black holes in entangled relativity are indistinguishable from the one of general relativity. There's a caveat, at least provided that the matter part does not correspond to a very specific type of dark matter candidate, because you could have another assumption. Instead of having the usual electromagnetic field, you can have some dark matter field instead. And in that situation, maybe you could have an effect. But otherwise, if you assume that you have pure usual electromagnetism, then you shouldn't have any effect difference of the waveform of the gravitational wave from the theory with respect to general relativity. So studies remain to be done for binary neutron stars. However, there may be degenerates with the various unknown equation of states that one can consider for nuclear matter inside neutron stars, which we don't know for sure. And therefore, whenever you have deviation from general relativity, it might be compensated by changing a little bit the equation of state. And therefore, naively, but studies has to be done, I don't expect that binary neutron stars, the gravitational wave from binary neutron stars, will constrain the theory a lot. I don't think that will be the case, but I may be wrong. Okay, now the actual good stuff. So sorry, I'm being a bit long, but the actual good stuff is now. So until now, I just tried to convey that this theory is, at least it seems, viable. Maybe not, but it seems that it is. So now, why am I excited about this theory? Well, for one reason is that I think, but this has to be proven precisely and mathematically, I think that singularities should not happen in this theory. And this is the reason. So basically, here is the equation of this theory, where here usually you have the 8 pi g over c to the fourth here. And you see that it means that this guy here is now gives kind of effective value for an effective constant of Newton, which now is a field, okay? And why, so if you look at this equation here, and if you are in a situation where this guy is equal to this, which is the situation like for dust that I talked about earlier on, then indeed you recover the Einstein equation, the trace of the Einstein equation. So it is consistent. The thing is that if this guy becomes positive for some reason, then you get repulsive gravity. So my conjecture is that this can happen inside black holes when matter becomes really high energy. Why is that? It does not come from out of the blue. It comes from the fact that usually matter density, the matter Lagrangian density, is defined as being the kinetic density minus the potential density. And therefore, you can expect, at least naively, that for in really high energy situation, this guy will become bigger than the other. Whereas in low energy limit, on the other hand, you would have that the potential energy is dominating. Anyway, it seems to show that there is a way that this guy can have his sign flipped at some point when the kinetic energy starts to dominate, starts to dominate. And if this happens, it seems that then repulsive gravity could happen. Therefore, the way I think it would work, and again, this is something tricky to study from a mathematical level, so might be wrong, but basically, you have the inside a black hole, you have this matter that condensates until it reaches a threshold where this guy has his sign flipped, and then you have repulsive gravity, and therefore you don't form a singularity. So again, this is, for now, it's only conjecture, but I think it is really exciting, really exciting. Same thing with the other issue that there doesn't seem to be any operational meaning of space-time beyond the Planck scale. And I recall that the reason for that is that because the radius of black holes is equal to 2 times g, the energy, and g being fundamental constant, g times the energy, basically. Okay, but that's no longer the case in this theory, because again, well, now you have the effective constant of Newton, which depends on this field. And therefore, the size of black hole now depends on the matter field equation that enters into this guy Lm. Basically, the effective Newton constant depends on the kind of matter field that you're considering. And therefore, now you have to be really careful when you talk about this kind of object, because you really have to solve the actual matter equation at really high energy in order to tell what happens to the effective Newton constant. Anyway, the Planck scale is not fundamental in the theory. So in any case, you shouldn't expect to have anything dramatic at this scale, because it's not fundamental. No, it is no longer fundamental. Sorry. There may be other issues, but at least shouldn't be related to the Planck scale. Which drives me to the next thing, which is actually there's a new scale in the theory, which is different from the Planck scale. Because until now, I didn't care at all about the dimensionality of this action. But it turns out that this action, because it enters into this phase, here, must have the dimension of an action, like the Planck's constant. Okay, Planck's constant has the dimension of an action, so an action has a dimension of an action. So if now one cares about, and why didn't I talk about that previously? Because at the classical level, one didn't care about it. It didn't change at all the field equation. So now if we care, we have a new we actually have a new constant here. which has the dimension of the Newton's constant, but not its value. Why not its value? Because this constant never appeared anywhere in the field equation, in the classical field equation, meaning that at the classical level, you don't care about this constant here. On the contrary, it is important for quantum field theory because it enters into the quantum phase, and therefore its value would lead to different predictions. But what it means that entangled relativity has a new purely quantum fundamental constant of nature, which at the same time is not related to the size of black holes, whereas it was the issue with the Planck constant for the fact that space-time didn't seem to have any operational meaning beyond the Planck scale. Is because basically the Planck scale is related to the size of black holes. Okay, so the consequences of this new constant has to be studied. Okay, so here is the chronology of entangled relativity again. Sorry. Okay, so that's the conclusion now. Sorry, I've been a bit long. What time is it? Yeah, I've been long. So this is general relativity, pretty simple, Lagrangian density. This is entangled relativity, pretty simple, Lagrangian density as well. We could argue about which one is the simplest. But the good thing with this theory is that it satisfies the three principles demanded by Einstein for a satisfactory theory of relativity, unlike general relativity, therefore. It possesses general relativity as a limited case whenever you have this, which occurs for dust or for null radiation or trace anomalies. That's a bit more technical. It has no free parameter at the classical level. And this is really kind of novel in this field, because usually when you have an alternative theory of gravity, you have plenty of new parameters. And the game, when you're testing those theories, usually is just to give constraints on the value of those additional parameters. You say, oh, from this observation, this parameter has to be less than this or more than this. And this is the game usually. Here, you don't have any fine-tune. Well, you don't have any parameter that you can fine-tune, that you can say, okay, this parameter has to be less if the theory has to be viable. Therefore, the theory is even, you can rule out the theory. There's no way you can escape that. That is said, this is provided that you actually derive from first principle what is the on-shell Lagrangian for matter, but that's a bit technical. But yeah, so it means that you can rule out the theory if you study it carefully enough. It seems that it can lead to small deviations that could be searched for, like with neutron stars, for instance. It seems, and I believe so, that that it has the potential to solve the issue of singularities, and also the potential to save the fate of space-time as an elementary structure of nature, and not as an emergent one, as many theoretical physicists have been arguing for decades. And it could probably be a description of a consistent framework for matter and gravity with, which is interesting, a new purely quantum constant of nature. Okay, now there are also many difficult things that remain to be studied, and each of which could be fatal for the theory. So I'm not claiming that the theory is correct, or describe nature correctly. There are many things that remain to be studied with this theory. So, for instance, the theory, the phenomenology of the theory remains widely unknown when the matter Lagrangian is different from the trace energy tensor. So when you're very far from the dust situation that I talked about, there must be a way to explain the acceleration of the expansion of the universe, because in the theory, there's no space for a cosmological constant. Cosmological constant cannot happen in the theory for some reasons. that are a bit technical that I won't discuss now, but happy to if you have questions. There's potential solution that I gave recently. The most important thing in order to test the theory and potentially rule out the theory would be to have the effective Lagrangian for messy fluids and have it from first principle calculations, meaning from microphysics, microscopic physics, and then derive the actual macroscopic physics. But this is really tough calculations, and therefore, but this is necessary if one wants to rule out the theory, in my opinion. Okay, so the other thing, what does the theory predict inside black holes? Because as said, I believe that the theory would not allow for singularities or near the Big Bang, because we expect that there's a singularity at the Big Bang. This is the Hawking-Penrose theorem. There are issues with, one has to check that the universal coupling that one assumes that the classical level is stable at the quantum level. This is, again, a bit technical, but this is a necessary condition in order to satisfy the university of free fall. You need to have that in order not to, well, in order to be consistent with the observation of microscope, for instance, the satellite microscope. More generally, what is the quantum field behavior of the theory is totally unknown, and it may have a lot of issues because of the specific form that it has. Although I'm pretty confident because, as I said, it can be rewritten in the form of scalar tensor theory, which has been widely studied already. So I'm not that worried about this. But something related is that should one expect the standard model Lagrangian to be modified to better fit into this new picture? And this is something that one indeed may expect. There should be some overlaps in the end between the standard model of particle and what you would put in the theory at a really fundamental level, at least when the theory becomes the same as general relativity in some limit. But yeah, that's a tough question. So this is it. Thank you for everyone. And as a simple reminder, we'll just say that I'm searching for fundings because the government of Monaco stopped my funding in 2020. So I'm looking for funding. So I don't expect that some of you may have some spare funding given the the current situation. But if you do, and if you think that what I do is interesting, then don't hesitate to reach out to me. Thank you.
Thank you very much. Thank you very much, Olivier. And I hope your call will be heard in the community very soon. So if you have questions, could you please raise your hand with the reaction button? I can see that we already have a first question from Simon Prunet. Can you turn on your camera and please ask your question? Go ahead, Simon.
Yeah. Hi, Olivier. Thank you very much for your very interesting talk. I have a question. You were saying that basically the effective Newton constant, who now is a field in your theory, freezes when you reach matter era. But what happens during the radiation dominated era, where you have it's behaving as a field effectively and coupling to the energy momentum tensor. So I would assume that it changes the perturbation theory for the metrics, and it should have an influence at least on the second order perturbation theory for the CMB anisotropies. So could you comment on that?
Yeah, sure. So basically, I don't know what happens during the radiation era. That's the reason why I didn't talk about it. I know what happens for sure during the matter era, but for the radiation era, I don't know, because basically, I don't really know how to model. I don't know enough of the physics of the radiation era personally in order to be able to really know what this guy would be. But if, for instance, I would assume that you have just null radiation in this era, then you get the same thing, meaning that you won't get a source for this scalar field. So if you assumed, which is not the case, but if you assumed that during the radiation era, you just have a null fluid, then you will get that during the radiation era already, you have the freezing of this scalar degree of freedom.
I see.
But this has to be studied. But I don't know enough of this physics to say things without without risking to say too much errors.
Thank you.
Right, Tristan, go ahead.
Yes, hi Olivier, great talk, and it's really a shame to learn that Monaco has stopped your funding. It's well, I hope we can find a solution. So I have a very naive question. Obviously, it's not my field at all. I was surprised to see that you can get these changes in mass for a neutron star, which is quite larger than the Planck scale, given that you were showing that that was a problem of GR. So you alluded to that in the fact that there's a length scale that's involved, and I was wondering whether your psi parameter was playing a role there. Is there an adjustable parameter that you can play with and you know,
Yeah.
modify this change in mass, or is it completely independent of that?
No, it's parameter free. Those results are absolutely parameter free. As I said, the new parameter doesn't at all enter into the field equations. That's the reason why I didn't talk about it until the very end of the talk. This parameter doesn't enter into the field equation, meaning that, well, basically you can take whatever you want at the classical level. You can take whatever you want, you will get the same result. So those results here are totally parameter free. There's one caveat, is that you assumed that, well, the assumption that I wrote previously, that you have this and therefore this, but you could have this as well, for instance. So that's the caveat. But using this assumption, which will have to be checked from the first principle, from first principle calculations, assuming that's it. You enter the field equation of your system and you do the simulation of the neutron star, and you will get this. And it is not related to the Planck scale. Well, it is related somehow, because the Planck scale is related to the constant of Newton. And here you have the constant of Newton that varies a little bit next to the neutron stars and inside the neutron stars. So here, basically, what you will have is what we see here is basically, well, here is the metric, but basically you can have kind of an intuition that the constant of Newton, the effective constant of Newton, will be varying here, whereas after it will become a constant. Sorry, I think I may
We
have
lost you a little bit, so
yeah.
you
So
may.
I'll say that again. I'll say the last 30 seconds. So
Thank you, Olivier.
I was saying that from this plot, this is not exactly the case, but you can have an idea of what is happening. You can see that the effective constant of Newton would be varying very slightly, really next to the neutron star, but not far away. Then it reaches a constant. And so, yeah, this is what you have regarding the aspect of the effective constant of Newton.
So of course, so the mass itself of the neutrons, the perceived mass, say at 1 AU, will be the same as in standard general relativity, right?
Hello. Okay, so first, and this is actually a good question, because it's a kind of tricky one. You have to find a new definition for mass, because now you have the effective constant of Newton that is varying. So how do you define the mass? And one way to do so is indeed to go at infinity. And at infinity, the constant of Newton is constant again in this theory, and therefore you can define a mass. And indeed, if you're far from the object, and you have, say, an object with this mass defined, you will get the usual Kepler equation for an orbit around this mass.
Okay. And so if we scale that to the sun or the Earth, what's the change that we
negligible? This is what was written here. You see, so you have the metric for integral relativity is equal to metric for general relativity up to modifications that are proportional to the pressure divided by the energy density, and it's 10 to the minus 10 for the Earth, which means that perturbation of relativistic perturbations would be at the 10 to the minus 10 numerical level, and there's no chance that you can observe those modifications. We don't have the precision in the solar system to test that. Although there's something that I'm putting under the rug, but it would become a bit too technical, and it's a study that we have not published yet, so I won't say more.
Okay, well, thanks a lot. Great talk.
Thank you.
Great results.
Any other final question? And it's already a little bit late, but it was an exciting talk by Olivier.
I think I have a very basic question.
Yes, go ahead, Axel.
So when you modify the action in the first place from the additive to the multiplicative form, is it already physically motivated, or is it that you try this new form and then you derive the field equations and see the physics after?
Yeah, that's a really good question. How did we come up with this specific form? And I think it's Feynman who said, when you're trying to find a theory, first you guess, then you compute what it predicts, and you say if it corresponds to reality, you say, oh, that's cool. Otherwise, you have ruled out your guess. Here, I have to go to the chronology of the theory actually to explain how did we find this. And it's kind of interesting by itself. So basically, in 2012, we found with a friend of mine, Aurélien S., that some scalar tensor theories could have an intrinsic decoupling, meaning, and this is what we've seen in this theory, is that basically in some situations you recover exactly general relativity because two terms exactly cancel out. Okay. And I worked on other things, but we know that usual scalar tensor theories are equivalent to another kind of theories called F of R theories. And therefore, I was looking at an F of R equivalent theory that would give this effective decoupling. And I was expecting to have, as usual, two Lagrangian, the sum of two Lagrangians, and it was just pure curiosity. But we, with Hendrik Ludwig, in the end, we found that, this action, where is it? Here. We found that this action, in order to solve this problem, in order to find an equivalent F of R theory that would have this effective decoupling built in, would look this way. And right away, well, it was really surprising, but right away, it was clear that it was something totally new and really interesting with respect to Mach's principle, because Mach's principle is something that has been debated over decades. A lot of people believe that it was really a big conundrum of general relativity not to be able to satisfy Mach's principle. And having a theory where you cannot even define spacetime without matter was really something that right away we liked. And therefore, yeah. So this is how we found the theory in the first place, by actually finding the mechanism that makes the theory equivalent to general relativity first. And then by doing some experiments, theoretical experiments, say, by trying to find action that would reduce to the other scalar tensor theory.
Okay, thanks.
I hope that it's understandable, maybe not, because
there are some parts that I did not get, but hopefully the presentation is recorded, so I can have a deeper look after.
Yeah, and don't to anyone, don't hesitate if you have any question to reach out to me. We can discuss about it.
All right. Thank you very much, Olivier. I will clap my hands on behalf of everyone in the list. And I think we can stop the recording and tell everyone that Nicole is going to be back next week, and she will be back on the seminar.